Okay, Assalamualaikum and a very good day to Dr. T and also to my faculty supervisor Dr. Zulfahanan and my fellow friend here inside this lab. So basically today what we are going to do is actually present my industry training progress. So this is my topic throughout 6 months here. So my topic is characterization of lignocellulose in oil palm biomass. Okay. So basically, here is actually my place of internship placement is actually in MPOP. So the history is actually Malaysian Palm Oil Board, or the acronym is MPOP, is a premier government agency under the Ministry of Plantation Industry and Commodities entrusted to serve the country's oil palm industry. So previously it's known as PORIM technology. Before it's been changed in 2001 to become MPOB. The vision of MPOB is actually to become the premier Nobel laureate in research and institution. So to develop our palm oil industry to a new high state. So the mission of MPOB is actually to enhance the well-being of the Malaysian oil palm industry, so that our oil palm industry can contribute to our economy. So basically, I was placed in energy and environment unit. Basically, there is about 6 unit of research, and energy and environment unit is one of the research unit. The energy and environment unit is one of the unit under the engineering and process research division of MPOB. So basically, in this division, few projects that have been done, such as production of the biodiesel, treatment of the pommy, and also the production of the waste treatment for the pommy. Next, so my project is characterization of lignocellulose in oil palm biomass. So the background of the study is actually the palm oil industry in Malaysia is regarded as one of the main contributors towards national economic growth. According to Abbas 2011, it was estimated that the total biomass production from fresh fruit bunch valued at 84.74 million tons. Among the biomass product produced from palm oil mill processing are empty fruit bunch, or we know as the EFB, mesocarp fiber, palm kernel shell or PKS, oil palm fronds OPF, and oil palm trunk. So basically, the OPF and OPT is actually come from a biomass that came from the tree, while the EFB, PKS, and the mesocarp is the biomass from the fruit. Okay, for the problem statement, the characterization of lignocellulose content in palm oil biomass is important, as most of the current biofuel and product are produced from lignocellulosic materials. Okay, this is really important because we have to know that these are going to be bring to the upper scale, which is actually economic scale, which will be used as an industry. So it's very important for the characterization of the lignocellulosic content in palm oil biomass. Okay, then we also know that each analysis that have been known to present dissimilar totally of lignocellulose. Like we know that we have a few standards that we refer, such as ASTM, AP, and REL, and some of the standards actually has been modified by some of the researchers. So all of this method is actually will make when we try to characterize the content of the chemical content of the palm oil become dissimilar between one research and the other research. So that's why we try to do this research, which is the objective is to explore and evaluate the available methods for characterization of lignocellulose content in palm oil biomass, and the next one is to compare the yield percentage for lignocellulose content in palm oil biomass. Okay, this is the method that we use for the holocellulose, alpha cellulose, and the hemicellulose. Basically, we have 3 methods. The first one is from Ling 2010, which is actually a revised from the ASTM method 2012. So the second one is Teramoto, which is developed by the researcher himself. The next one is then 2014. It is also been modified by the researcher by himself. The next one is lignin. For lignin, we are using three standard. Which the first one is Kirk 1980, which is developed by the researcher. The next one is based on ASTM, reapproved on 2007. That is among the latest characterization of lignin in 2007. The third one is Lee 2004. Okay. So for result for holocellulose, we can see that the yield percentage for all sample in method 2 is higher than method 3. We can see from this graph. For all sample EFB, mesocarp fiber, all palm front, OPT and PKS, the yield percentage for method 2 is higher than method 3. So basically method 2 is actually done 2014, while method 3 is Teramoto. So for method 2, EFB and OPT yield a high percentage for holocellulose at 76.8% and 79.4% respectively. For method 3, OPF achieved the highest yield percentage for holocellulose at 62.7%. It's shown based on statistical analysis that as we using ANOVA, it's shown that only EFB, mesocarp fiber, OPF and OPT have a significant difference between the method 2 and method 3. We can say that actually most of the sample is actually have a significant difference. Okay, since most of the sample have a different, we can say that they actually they have some problem. It's not problem, but maybe dissimilar between the usage of the solvent that used, because in method 2 we are using sulfuric acid, 1 mole of sulfuric acid, while in method 3 we are using acetic acid, a pure acetic acid around 100%. So it may be that the difference in concentration have resulted in a different yield percentage for each method. So for alpha cellulose, we have to understand that the alpha cellulose is actually extension from the holocellulose experiment. So for method 2, the highest yield is percentage of alpha cellulose is EFB, we can see, which is with the percent is 54.341. For method 3, the highest alpha cellulose yield is EFB and OPF with the value 35% and 30% respectively. The result shown that only EFB and OPT have a significant difference between the methods. Okay. The next one is result for hemicellulose. So the method 1 is the only experimental is the only analysis that had been done to analyze the total yield percentage of hemicellulose. Because for method 2 and method 3, we just calculate the difference between the holocellulose and the alpha cellulose that we have done before. So for method 1, the sample with the highest yield percentage of hemicellulose is OPT with the value 28.29. For method 2, the highest yield of percentage of hemicellulose is mesocarp fiber with value 33.19. Mean yield percentage value of hemicellulose shown that EFB, OPF and OPT are within the range reported by Siana 2018. For method 3, the highest yield percentage of hemicellulose are OPF and OPT with value 28.5%, 28.4% and respectively for OPF and OPT. Okay, for lignin, we can see that actually the highest percentage of lignin is actually PKS. This is actually logic because we do know that actually PKS have a very high content of lignin, high content of lignin compared to cellulose component. So that's why we can see that all three methods show a high percentage of yield percentage of lignin between all three methods. So all methods show a good repeatability because all the standard deviation is below than 5. It's only that mesocarp fiber, OPT and PKS show a statistical difference between each method. Okay. So as a conclusion, it is concluded that each method have a different yield percentage of lignocellulose content in the palm oil biomass due to different in method approach. So what is meaning by the method approach is actually what is the type of solvent that have been used, because the type of solvent that we use is going to digest the component of the cellulose of the lignin to get the yield percentage. Next, also we have to okay, that's what the meaning by the method approach lah. So that's it. Thank you from me. Got a question?
Oh, go back to your problem statement. Thanks for your presentation. Okay. This background.
The background.
Hmm. Okay. What is the application for cellulose?
Application of cellulose. Okay, basically cellulose is being used basically for production of bioethanol or ethanol. That's one of the way. I mean it's actually to know the percentage of of cellulose. Okay, that's the first. The second one is actually the cellulose is really we can use as a pulp for a paper. We can use as a component inside a paper. That's one of the production of cellulose lah, for us to characterize.
Okay. So for this one, this is methods for.
Yes, this is a method for
cellulose.
cellulose. Yes.
So just now you mentioned which one is the best method?
Okay. For
cellulose.
alright. For cellulose. Okay, we can say that actually the best method is actually for method 2. Method 2 because we can see that all the yield percentage is high and within the range that has been reported by the previous study. Okay, what we can say is actually the type of the solvent that been used to diagnose the component because for method 2 we are using just a very low concentration of sulfuric acid, which is 1 mole. So when the 1 mole is actually being used as a pH to adjust the pH of the solution to mimic the acidic condition. So meanwhile for acetic acid, we are using a very pure acetic acid with concentration around 98 to 100. So it may be because due to the high concentration of the acetic, we can see that the yield percentage is really low, especially for mesocarp fiber and also for the OPT. If we want to compare with the method 2, which are using the sulfuric acid with a low concentration at 1 mole, the yield percentage is very high. So we can say that actually the difference in the solvent that has been used is actually can contribute to its, whether it is will produce a high yield percentage of the component that we want to find, or it's going to give us a very low percentage of yield percentage that we want. So that is the reason for the different in yield percentage. So as to answer your question, which one is the best? Is actually both is actually good. Actually, to use acetic, we can still use acetic. We can use sulfuric acid, but the good way is actually to find a proper concentration. We cannot use a too high concentration, but not too low. So that's why some of the researchers are using sulfuric acid 72% because that is the most optimized concentration to hydrolyze the component of the cellulose or lignin. So we already have the validated concentration that we use. So it must be within the range. It cannot be too high or too low the concentration.
Okay, is the result for method 3 same with the previous studies?
Some of the sample is within the study, but some of the sample is not. For example, mesocarp fiber. Mesocarp fiber is really low than the expected from the previous study. Yes.
But for method 2 is almost the same with the previous studies.
Yes.